Good morning, sir.
Okay. So till now total 21 students have joined. I'm going to take the attendance. Take the attendance. Let us go to the speech element. First of all, please confirm whether my slide is visible or not.
Yes, sir.
Okay. So just giving some recap the things what I have discussed last time. I was actually discussed mainly about the PSCPS. So as we know, as I told you, that PSCPS is called as pseudo noise random code, and it is in fact in instructions deterministic in manner, whereas for our actually calculations and for our applications we assume it as a purely random in nature. Okay, so how can we generate this? We can generate, and the basic applications of this PS sequence we have already seen that we used to in the spread spectrum techniques to spread the spectrum of the modulated signals, and in that we have already seen in the direct sequence spread spectrum techniques. So how can we generate it? We can generate it with the help of flip-flop of shift registers and numbers of flip-flop or number of shift registers we can use, and by using the example logic circuitry. So if there are n numbers of flip-flop, then total number of maximal sequences what can be generated will be 2 to the power n minus 1. So since here there are 3 numbers of flip-flop or shift registers, so we get n equals to 7. So you can see the 7 output we got. Okay, in basic operations I'm not going to tell you because in more details and previous to previous class also I've already discussed about this circuit, and we get this maximum 7 7 chip maximum sequence code. Okay, so if the clock speed is given by RCH, then the chip period, this chip period will be given by 1 upon RCH. Similarly, we can say that if one chip duration is TCH, then period after which this repetition will occur, that is given by Tn equals to n into Ts if there are n number of chips. Like in this particular case, there are 7 number of chips. So, and as we have seen that there are number of ones are always more than number of zeros by 1 if we take this particular arrangement. In the mirror image case, the number of zeros will be more than the number of ones. Then we have talked about some properties of the this one PLC case, where we have seen that this property I have already told you that the number of ones is more than the number of zeros. And the second property you can also put it this one, that is the DC offset level is very less and it is close to 0 because approximately the number of ones and number of zeros are equal. So the DC level is very close to the 0. Then after about the second property, or you can say the third property, that the number of maximal sequences what are possible with the given circuit is given by phi n by n, where phi n is the Euclidean functions, which is actually having the value in the integer range of 1 to 3 up to n minus 1, which is relatively prime to n. So for that, how can we calculate this phi n? Phi n we can calculate with the help of this formula, where p1, p2, pr are the prime factor of n. So for that we have taken the example that if the number of flip-flops or shift registers are 8, then capital M will be 255, and the total prime factors of this 255 are 35.70. Correspondingly, we can choose the P1 as 3, P2 as 5, P1 as 3, P2 as 5, P3 as 17, and we can calculate this phi 255, which is coming out to be 128, and phi 128 divided by 8 will be nothing but the 16, and as the 16 total number of 16 maximum sequences are possible. And we can even take a simpler example considering the case of n equals to 3. So corresponding to that, capital N will be 7, and there is only one prime factor, that is 7, and from that we can calculate the maximum sequence maximum number of possible sequences, which is coming out to be 2. That is 1 and 2. Now, then we have seen that autocorrelation functions. So once the same actually PN sequence is received, then we get that autocorrelation function value by which we can calculate. That is, this one is the PN sequence, and the shifted value of the PN sequence is first multiplied, then integrated over the one cycle, and it is coming out to be maximum when there is no time lag or time lead or time delay. Okay. Otherwise, if this tau increases, that is this delay increases, this decreases by the factor of 1 by n. If we normalize the peak value to 1. So these things we have already studied. Then we have talked about little bit. We have talked about Cdma, and at the starting I told you that this Cdma is nothing but one of the application of direct sequence spread spectrum. So here, if you talk about the applications of direct sequence spread spectrum, then two applications will be studying. One is the Cdma, and another that is to find out the range of the target. So after discussing the Cdma, the second applications I will be discussing, that is how to find out the range of a target. And the basic introductions about to find out the range of a target I have already discussed last time. Okay, so that is next one of the applications, that is applications of the direct sequence space spectrum, that is called as Cdma, which I am going to discuss. So this you can see, as the name suggests, this one Cdma is the multiple access. So one of the applications, like if you talk about the modulation, then we might have studied that with the help of modulation we can get the multiplexing. Okay, that's this is one of the applications of the advantages of the modulation, using the modulation techniques in the communications. That is the multiple access techniques. The technique is possible. So time division multiplexing, frequency division multiplexing, and those two multiplexing techniques you might have already studied in the ACS class. Similarly, in the direct sequence spread spectrum, the multiple access technique is possible. That is, in the multiple access, what happens? Last time I told you that three axes if you consider, and this axis we consider as a code, this axis we consider as a time, this axis we consider as a frequency. Then, if we transmit, suppose in the satellite communication, if it there are a number of users, that is the transmitter, and there are a number of receivers, that are receivers, and they can even transmit and they can even receive. Duplex type of communications is there. Now you can see, if we make this, if the transmitter uses the transponder of this satellite, utilizes the transponder of the satellite at the same time, but using a different frequency band, then that type of multiplexing technique, using the same code obviously, then that type of multiplexing technique is called as FDMA, frequency division multiplexing techniques. And if the transmitter utilizes the transponders with the same frequency, taking the same frequency band, using the same code, but using the different time slots, then that type of multiplexing technique is called as TDMA, time division multiple access techniques. But these suffer certain drawbacks. It does not mean that both are not being used. Both are being used. Okay. So this TDMA suffers mainly that tedious synchronizations is required to synchronize that in which slot actually that transmitter needs to transmit. So next one is called as CDMA. That is, in CDMA, if you use the same frequency band, that is the same carrier throughout, and at the given time or at the same time, if you use the different codes, if different codes are being used by the different transmitters, then such type of multiple access techniques are called as CDMA, that is code division multiple access techniques. And this CDMA, design of the CDMA is possible with the help of direct sequence spread spectrum techniques. Okay, so in CDMA, in short, we can say that if suppose there are numbers of transmitters and numbers of receivers, okay, then they transmit the signal at the same frequency and at the given time, that is at the same time, but by using the different code. And which type of code they used to use? That is nothing but the PN sequence. Now suppose this is the first user, this one is the first transmitter, this one is the second transmitter. So suppose this one uses the PN code as G1T, this one uses the PN code as G2T, similarly this one uses the PN code as G8T. And we assume here in the second case that all the transmitter transmit the same power, that is PS. Transmit the same power PS. They transmit using the same frequency band, and that is the carrier frequency F0, and at the same time. Then what will happen? This they may use the cellular communications or they may use the satellite communications. So at the satellite, this after receiving these signals by the satellite transponder with the help of transmitting antenna, that it is transmitted, and receiver, a lot of receivers are there. So each receiver experiences the signals because of the all transmitters. So these receivers will be receiving the signals transmitted by transmitter 1, transmitter 2, and so on, transmitter I, R, N, or K. Suppose there are K number of transmitters. So this will be GKT. So all the signals what will be received to the receiver 1 will be the sum of the signals transmitted by all the transmitters. Similarly, the receiver 2 also will be receiving all the signals. Similarly, the receivers, suppose there are n numbers of receivers, so that another receivers will also be receiving the sum of all the signals. Then, if this one is receiving the sum of all the transmitted signals, then how can we, now suppose this one is intended to receive the signals transmitted from the transmitter 1, or this one is intended to receive the signals from the transmitter number I, in between I, then how can we recover? Because that message signal what is being transmitted from the transmitter I should be received by the receiver 1 only. But in fact, this receiver 1 is receiving the K numbers of transmitted signals. So it is the job of the receivers to actually extract the message signals, that is the information signals, from all the received signals. So we will see over here that how can we extract that message signals from the transmitted signals, and what will be the nature of the received signals at the receiver part. Here we assume, in fact not we assume, that that carrier frequency all the transmitter is same F naught. The assumption is that all the transmitter transmit the same power, that is the PS. Okay, and at the same time we are assuming that all the G, that is the pin sequences what they are using, that are having the chip frequency FC, that is the equal chip frequency they are using, and the transition of suppose one pin sequence is like that, another pin sequences may be like that, but we assume that the transitions at each bit should match. There should not be any offset in the transition. So these are certain assumptions which we are following, and in fact these assumptions, taking these assumptions is not is actually not as practical, because this transmitter, this satellite what we use, that is the intermediate device what we can say, which is receive the signals from all the transmitter, and then this transmit it again with the transmitting antenna, and it receives the signals with the receiving antenna. Now, it is not necessarily that in the case of satellite communication, it is not necessary that all the transmitters transmit the signals further with the same equal power, say PS. But if you have the direct communications in the cellular communications, then we can use directly. That is, this PS transmitted from the transmitter 1 is directly received to the receiver 1, and similarly by the receivers 2. And that is, all transmitter may use the equal power. But in the satellite communications, although they are using the equal power, but since all the transponders what are being used to transmit further these signals, that may not transmit with the same equal power. So this analysis may not be so accurate in that particular case, but rather than in the direct cellular communications and all. But and in fact, if that assumptions hold correct for the case of satellite communications, that is, all the transponders utilizes the equal transmitting power, and in that case we can say that this analysis is correct. And at the same times, the second one, second drawback of this assumption, considering this assumption, is that this CDMA suffers the near far problem. What is near far problem? And this near far problem appears since we have assumed that our transmitter transmit the equal power. Do not happen in the cellular communications type. What happens? Suppose this signal, this transmitter 2, transmit the signals to the receiver 2. Suppose this transmitter 2 wants to transmit the signals to the receiver 2. Then what will happen? Since this receiver 2 is far from this receiver 1, and this receiver 1 is more close to this transmitter 2, then what will happen? this power received by the transmitter receiver one will be more because this one is transmitting with the equal power PS, with the same power PS. So this power was it is transmitted, the receivers which is far from this transmitter will receive the lesser power as compared to the receiver which is nearer to this transmitter. So this receiver may think that okay, this signal is intended to me, and these receivers can detect, and sometimes sometimes the error can occur to the receivers too. That error is called as near far problem or near far error, and that error in fact appears because of the near far problem. But nowadays this problem can easily be rectified. How can we rectify? Just by using the adaptive power control system. That is the transmitter which is nearer to that receiver will need to transmit the lesser power as compared to the receivers which is far from that transmitter. So this unequal power transmissions can be done with the help of adaptive power control. But in our analysis, where we have assumed that all the transmitters are transmitting with the equal power of PS, that will definitely suffer with the near far problem. And this near far problem, in fact, is actually minimized in the case of frequency hopping spread spectrum. So these are some characteristics of the multiple access techniques and some drawbacks. So as I told you, then we will go for the mathematical analysis, and we will see that if suppose the one transmitter transmit the signals for any one of the receivers, then how we can receive the signals, how can we detect that particular message signals, and at the same time, if that signal is received, then what is the chance of error? That is called as probability of error, and we'll be calculating that also in the case of Cdma. Okay, so looking all these in mind, I'm just going to first delete the things what I've written. Okay, so looking considering all those in mind, we here describe the method of multiple access communications, which on principle allows more than one sender use the same channel for the transmission. Same channel means they are using the same carrier frequency and same frequency band for the transmission. But definitely, as yesterday I told you that there is a chance of the collision, and when it is being sent. So, but collision is actually such a thing that that the error occurred because of that collision is very small, and with the help of error corrections coding, with the help of retransmitting the signals and asking the transmitter to transmit it once again, that error further can be minimized. This scheme employs the spread spectrum and is called as code division multiple access techniques. As I told you, the advantage of the Cdma system is that collisions are not sensitive. This collision which may occur during the transmitter because they are utilizing the same frequency band and they are transmitting at the same time, all the transmitter. So, but the collision may occur, but that collision are not so sensitive. That is, each of the signals involved a collision would be received only with a slight increase in the error rate. So, in the Cdma, each user is provided with an individual and distinctive PM code. As I told you, that suppose we are discussing about the satellite communications, so there are number of transmitters and there are number of receivers. Okay, and each transmitter is assigned to the distinct PN code. Like in this case, it is assigned as G1T. Second transmitter is assigned to the G2T, and if suppose there are k number of users which are transmitting, then the kth will be assigned as GKT. So in Cdma, each user is provided with an individual and distinctive PM code. These codes are almost uncorrelated. That is, this G1 and G2 both are uncorrelated. There is no such similarity between these two. But the chip frequency for all the peer sequences remains same. That is the FC. And at the same time, we assume that the transition from one chip to another chip for all the bit happens simultaneously. That is, in Cdma, each user is happens at the same time. Okay, so in Cdma, each user is provided with an individual and distinctive PM code. These codes are almost uncorrelated with one another. For the purpose of our explanations, we all assume that the sequences are indeed uncorrelated. Okay, so for all our calculations, we'll be assuming that all these G are all these G are uncorrelated to each other. So to illustrate the principle of operations of Cdma, consider that at a given time, Okay, each K user is transmitting the data at the same carrier frequency. Actually, that is the characteristics of the CDMA. That is, here we need to utilize the same carrier frequency band at the given time, that is at the same time, using the DS, direct sequence spread spectrum. And his particular code GIT, that is GIT is nothing but G1, G2, G3. If there are K number of users, then I will vary from 1 to K. Then each receiver is presented with the same input form. That is, each receiver will receive the signal from transmitted by transmitter 1, transmitter 2, transmitter 3. Then what will the mathematical expression of the signals received by the receiver? And since we are using the direct sequence spread spectrum, so definitely the mathematical representation of the direct sequence spread spectrum for the transmitter 1 will be nothing but under root PS, and then G1T because of the transmitter 1, and DT, they best transmit the different data. So you can write it as G1P, then cos, they are using the same carrier frequency, so omega naught T into cos omega naught T plus theta I, because the phase change because of the R transmitter may differ, and this phase is also uncorrelated to each other. So this is the signal. This signal is transmitted by the transmitter 1. Similarly, the G2, D2, and theta 2 will be transmitted by the transmitter 2. Similarly, transmitter K, it will be replaced by K. But all the signals will be received to the receiver. It means that these signals will be nothing but the summation. So the signal which is received by any one of the receiver will be summation I equals to 1 to K, because K number of users are transmitting. We have assumed that there are K number of users. So since K number of users are transmitting and it is received by cell receivers 1, the under 2 PS, not PS, sorry, it is under 2 PS, normalized power is under 2 PS, then GIT, DIT cos omega naught T plus theta I, because the phases may also differ by from each transmitter. So this VT is nothing but the sum of the DSS, that is the sum of direct sequence spread spectrum signals received from all the transmitter. So here, what are the symbols we have used? That is, each signal is assumed to present the same power. As I told you, that this is our assumptions. That is, each transmitter is transmitting with the same power PS, and because of this only, that near far problem happens. Because the receivers which is nearer to that particular transmitter may receive the higher power as compared to the receivers which are far from that particular transmitter. So because of that, the error may occur, and that is called as near far problem. And this one is the serious problem of the CDMA. But nowadays, this can be simply minimized with the help of adaptive power control system, which actually transmit the unequal power depending upon the distance of that receivers. So each signal is assumed to present the same power PS to the receiver. This is our assumptions. And each pseudo-random port GIT has the same chiplet. This also I told you that this one is having same chiplet FC, and the data what they are sending, that data is having the same bit rate, that is FB. So each pseudo-random sequence GIT has the same chiplet, and DT is the data transmitted by user I, and data rate FB for each user is same. Right? Not DT, here you can write it as DIT. DIT is the data transmitted by user I. So it will be D1T for the first user, D2T for the second user, and DKT for the kth number of user. So and the data rate for all the information what are being sent from the various transmitter remains same, that is FP. So all GIs are having the same chip rate, all DIT are having the same bit rate FP. Okay. And also theta is the random phase. This theta is the random phase, statistically independent of the phase after each user. That is the theta, which is the phase change by the transmitted signals that are independent to each other, and the theta may be the random in nature. And thermal noise here we have ignored for the purpose of our simplification of the discussion. So this you can say is the mathematical representation of the CDMA signal. You can say this is the mathematical representation of the CDMA signals. Now, same expressions I have written again so that you can visualize this expression in this particular slide. Now, how can we detect? Then question arises that if this signal is received by there are number of transmitters, there is a satellite, and there are number of receivers. So now suppose this signal is received by say receiver 1, then how can we detect? Because this receiver is intended, suppose, to receive the informations D1T. So how these receivers can actually receive the signals or detect the information signals from the transmitter 1? So for that, we can use the same receiver circuit of direct sequence spread spectrum. And in the direct sequence spread spectrum, we have seen that first we multiply it with the G1T, and then we multiply it with the carrier signals having the under 2 cos omega naught t plus theta 1, because the phase change by the transmitter 1 will be theta 1, and then we pass it with the integrate and dump circuit. So using the same circuit, actually, we can receive the data transmitted by transmitter 1. But suppose if this receiver 1 wants to receive the signals transmitted by transmitter 2, then here again we need to have the correlator, that is here we need to multiply it with G2T, and then we need to multiply it with the carrier signals cos omega naught t plus theta 2, and then we need to use here the integrate and dump circuit. So if there are k number of users, then there should be k correlators at each receiving side, so that this receiver can receive the data from transmitter 1, transmitter 2, transmitter 3, and transmitter k. So this is how this data is received. So now suppose here we have assumed that suppose this receiver 1 wants to receive the signals, then this receiver 1 will multiply it with the G1T, and suppose this receiver 1 wants to receive the signals from the transmitter 1. Then this receiver 1 will multiply with the G1T, because all these correlators are parallelly connected, and these signals will be received by the bank of these correlators. So depending upon that, which definitely if that signal is coming from the transmitter 2, then and if this receiver wants to receive that signals from the transmitter 2, then it needs to multiply it by the G2T. So under PS, so here suppose 1 wants to receive the signals from the 1, then here we can multiply under PS G1T, then GIT as it is under 2PS. So I will let you know that where under 2 term has 1. So under PS, then GIT is over here, and before that it multiplies with the G1T. So G1T is here, then DIT is here, and then cos omega naught t, and then in this cos omega naught t further multiplied with the under 2 cos omega naught t. So if you multiply it with the under 2 cos omega naught t, then under 2 will be 2, and cos omega naught t plus theta I, and then cos omega naught t plus theta 1. The difference term will be nothing but theta I minus theta 1, and another will be suppressed by this integrated dump circuit, that is simply acting as a low pass filter. So the output of this low pass filter, we will be getting this signal only, right? This signal only. Then and this signal now this signal we can represent by this expression. How? If you consider I equals to 1, then it will be nothing but under PS, then G1T, and then DIT, and then G1T, because under 2PS G1T is there, and I equals to 1, then G1T, and we know that G1 square T is nothing but 1, and then here it will be D1T, and then cos theta 1 minus theta 1, cos 0 1. So the first term corresponding to I equals to 1 will be nothing but under PS, then D1T, because G1 square T will become nothing but 1, because we know that the PS sequence multiplication of both are energetic data, and both are having the transition at the exactly same time, then the square of that one will be nothing but 1, and that will be 1, and we have under PS D1T plus summation I equals to 2 to K under PS G1T. This will be as it is, then GIT DIT cos theta I minus theta 1. Now Looking to this expression V10 dash, you can say that since this receiver wants to receive the signals transmitted from the transmitter 1 and the information, that is the message signals what has been transmitted from the transmitter 1 is nothing but D1T, and that one is related to, is associated in the first term, that is V01 dash equals to under PS T1T. So this is related to the information signals what has been transmitted at the transmitter 1, whereas other signals will be acting as an interference signal. And because of this signal only, if there is some chance of the error, so that error occur only because of that error may occur only because of these signals. And the probability of error we can calculate considering these signals. The probability of error we can calculate as we have already calculated by considering the case of single tone interference and jamming concept. Because if we go back to that slide, that is of the single tone interference and jamming, then we can see that here you can see we have considered in the case of single interference, single tone interference and jamming, this is nothing but a sinusoidal signals, which is actually acting as an interference to that of the message signals. So for that we have done the analysis, and we have seen that the probability of error was coming out to be how much? Probability of error was coming out to be this, or we can say this. So similarly, but the difference, what will be the difference with that analysis and with this analysis? The difference will be, I'm coming to the current slide now. Okay. Now, the difference will be that there was only one sinusoidal signals, but here the sum of k minus 1 sinusoidal signal, because I starts from the 2 to k corresponding to 1, we have written this expression. So there are k minus 1 terms. So all the transmitter will, suppose this receiver will receive the signals transmitted by the power, transmitted by the each power, transmitted by the power by each transmitter. So only the difference that there was the term of Pj that will be replaced by the sum of power transmitted by R transmitter k minus 1 transmitter, that is k minus 1 Ps, and the rest of the actually calculations and analysis will remain same, and we can directly use those expressions what we have already derived in the case of single tone interference and jamming. So here I was actually I wanted to tell you that V01, which is the signal received by the first correlator, output of the first correlator, or you can say the output of the low pass filter integrated and dub circuit of the first correlator, is gained by this one. And that correlator actually based on the data D1T, thereafter after this integrate and dub circuit, we used to use the decision making device. And this decision making device where we set the threshold level, say for example, if we set the threshold level at lambda equals to 0, then if this received signal is more than lambda equals to 0, then that is decided by 1, otherwise it is decided by 0. But due to these signals, there may be error while making the decision. So that causes the probability of error, and that we can calculate in a similar way as we did the analysis for the single tone interference and jamming signal. So how can we calculate that? So for that we have represented this signal by another expression. By another signals like V01 dash equals to under PSDT. So this is nothing but our information signals. Summation I equals to 2 to k, I equals to 2 to k under PS as it is. And then here it is G1T, GIT. So this is nothing but another PN sequence, because this will be nothing but another PN sequence, because we have assumed that a transition at each edges chip after each chip period is at the same time. So this G1T multiplication with the GIT will give another PN sequence which will also be having the same chip rate, if we assume that their transition happens simultaneously. So that both are having with the same chip rate, so we can we can replace this G1 to GIT with another chip rate, another PN sequence that is given by G1IT. And similarly, the difference of the phase, this theta I minus theta 1, we can replace it by theta 1I. So these expressions we can write by this one. And now if you look to these expressions, this expression is very much matching with the analysis what we have considered in the case of single pole interference in Jamming. Because if you look to this expression, then this expression is the same expressions what we have derived, what we have taken in the case of interference in Jamming under Pj gt cos theta. And here this expressions, if you look, then this is also the same, that is under Ps G1I t cos theta 1I. Only we need to consider this Pj in these equations, which is nothing but the k minus 1 into Ps, because this receiver receives the signals what are coming from the k minus 1 numbers of transmitters. So comparing these two, and we have already calculated the power spectral density for this particular signals. And then we had already calculated the probability of error for this particular interference signals. So same expressions we can apply over here. So if you look to these expressions, then the probability density functions, power spectral density, we have calculated to this one for this particular condition. If you recall the concept what I have discussed, if you could recall the concept what I have discussed for the case of interference, single tone interference signals. This was the energy data. So for energy data, we are having the single square functions of the power spectral density, and then if we consider that mod of f less than equals to fb, then we can approximate it by the amplitude portion, that is the constant value, that is Pj cos bar square theta by 2fc, and cos bar square theta is nothing but half, and Pj we can replace by k minus 1 Ps. This Pj we can replace it by the k minus 1 Ps, and cos bar square theta is nothing but half. So we can calculate Gj further. Which is given by Pj. Pj is replaced by k minus 1 Ps, and cos bar square theta is replaced by half. So it will be 1 by 2 fc. So this is the expression we can say, that this is the expression we can say is of power spectral density for n numbers of sinusoidal signal, not n, k minus 1, some of the k minus 1 sinusoidal signals. Okay, sinusoidal signals. So this is the power spectral density, that is k minus 1 Ps divided by 4 fc. When mod of it, this must be satisfied. So now we can use this power spectral density expression to calculate the probability of error, because we can equate it by eta by 2, and then we can calculate eta, and then we can use the probability of error as half complementary error functions under EB by eta, or we can directly use the probability of error what we had calculated for this particular case, and there we can replace this Pj by k minus 1 Ps. So both way you can actually calculate the probability of error for the Cdma, for division multiple access. So here we have simply replaced this Pj to k minus 1 Ps, and by using the same expressions, because from the discussion of the single pole interference and jamming, we had calculated the probability of error by this expression. So if in this particular expressions, if we replace this Pj by k minus 1 Ps, then that expressions will be the probability of error for the Cdma. So that we can write, if we replace Pj equals to k minus 1 Ps, then for the Cdma, the probability of error will come out to be half complementary error functions under root 2 1 upon k minus 1, because this Ps and Ps will cancel out, and Pj will be replaced by k minus 1 simply, and 2 will be as it is, fc by fp. So the probability of error will come out to be half complementary error functions under root 2 1 upon k minus 1, where k is nothing but the number of transmitters, and fc by fp. And fc by fp in single term, we can simply tell it as processing gain Cp. And in this case also, the processing gain we prefer to have the as high as possible to minimize the probability of error. Or we can derive another condition also, that is, if this factor is much greater than 1, then also the probability of error will be less. And from that, we can actually derive the condition that if fc by fp divided by k minus 1 by 2 If much greater than 1, then definitely this probability of error will be less. So it is given as fc by fb is much greater than k minus 1 by 2. So this condition should be satisfied to get the full value of the probability of error, to minimize the probability of error. Now, as I told you, that in equations of Vt, we assume that now these things I've already told you in the starting of the class, in the starting of the today's class. That is in the equation of Vt. That is in this equation. It is talking about this equation. I'm going to that. I'm going to the previous slide. This equation. In the equation of the Vt, we have assumed that all transmitters are transmitting the equal power, that is Ps. All the transmitters are transmitting the equal power Ps, whereas in the satellite communications, once these signals are received, the transmitter transponders may not actually transmit the equal power. So this analysis may not be as much accurate in that particular case. Okay, so in the expression of Vt, we assume that each transmitted signal presented the same power Ps to the receivers. There are many practical situations where such is not the case. When transmitting to satellite, especially when transmitting to satellite, there may be high power as well as low power transmitters. Also, in ground communications, one user may be close to the receivers while another may be far from the receivers. That is, this one is the satellite. So, if we talk about the relative to that satellite, most of the user will be actually will be of equal distance, because we do not actually see that from the satellite this side is same, this side is same. If this was the geostationary satellite, which is mainly used for the communication purposes. So, but this happens for the case of cellular. This may happen for the case of cellular communications. That one receivers may be very close, another receivers may be far, but they may receive the unequal power. That is, the receiver which is very close to that of the transmitter should have received the actually in practical sense should have received the should have required the lesser power to detect the signals, but in fact that may receive the higher power, because if the receiver which is intended to receive that signal is far from the transmitter. So when an unwanted users, that is, these are the transmitter, these are the receivers. Suppose this transmitter is not, am I audible?
Yes, sir.
Actually, I got disconnected as I received a phone call from the dean of student person. So, but we are on the completion of this particular topic. That is, this one was last paragraph which I tried to discuss. That is when an unwanted receiver, that I was explaining that this one is the satellite communications. This one is not satellite. This one, these are the transmitter, and suppose these are the receivers. Now, suppose this transmitter one wants to transmit the signals to the receivers too. So it will transmit, but since receiver one is nearer to this transmitter one, so this may receive larger power as compared to the transmitter two. So this problem is called as near for power problem. So for this signals, this receiver 2 is nothing but unwanted receiver. So you can see when an unwanted user, that is the user 1, receive the power is much larger than the received power presented by the desired user. That is, when unwanted receiver receive the signals much larger than the receivers where for which the transmitter the signal is intended, then error can occur. And this problem is referred to in the literature as near fall problem, and limits the utility of DS systems to applications where each user receives power approximately the same. In modern systems, this problem is addressed by adaptive power control. So these things I've already told you in the starting of this topic. That is, this near power problem is not as, nowadays it is not as serious as it was earlier, because with the help of adaptive power control is adaptive means that system can adapt according to your requirement. So here the requirement is that system should transmit the transmit lesser power to the user which is nearer to the transmitter, and more power to that of the receivers which is far from the transmitter. So that can be done with the help of adaptive power control. So now it is going to be 11:50. So I'm not going to start another because next application. Okay, let me discuss the advantages of the Cdma. So this is some advantage. I've already told you that interference of the rejection property, multipath interference, synchronization between stations in the system is not required. As I told you that in TDMA, the main problem is that of the synchronizations where each time slot should be synchronized with the transmitter as well as to the receiver. So that such type of bulky and complex systems are not required in the Cdma. The degradation of the Cdma reduction in the signals to noise ratio is gradual with an increase of the number of users. That is, suppose there are k number of users, and as population increases, after 1 or 2 years, some more numbers of users can be added in that system. Then the degradation of the signals to noise ratio is not actually is gradual. It is not right abrupt that if the from k to 2k number of users have been connected, then lots of EB by N degradation is there. So if this EB by N naught will not reduce by the large amount, then definitely that probability of error will not increase. So, but the main disadvantage of the Cdma is the low throughput efficiency. And nowadays we cannot put that near far problem of that Cdma as a drawback, as a disadvantage, because that can be addressed by the adaptive power control. So the main disadvantage is the low throughput efficiency. So with this, thanks to all of you, and in the next class, I will be discussing the second applications of the direct sequence spectrum, that is called as ranging using DS spectrum. So with this, I thanks to all of you, and at the same time, I request you all that if you have any doubt, please ask me. Otherwise, we can end our discussion over here. Please. Anyone of you?
No, sir.
So let